Night is older than humanity, older than dinosaurs, older than complex life itself. For 4 billion years, Earth has turned, half bathed in sunlight, half wrapped in darkness. That rhythm might end soon, not from war or climate, but from an object currently diving into Jupiter with density readings that violate every natural formation model we have. They're calling it 3i Atlas, but that name feels inadequate for what it might actually be. A catalyst, a trigger, a spark aimed at turning a gas giant into something that glows. Stay until the very end, because we're about to show you what happens when your sky gains a second sun and darkness becomes extinct. If you're as captivated by these cosmic mysteries as I am, go ahead and like this video and subscribe to stay with us as this story develops. Leave a comment telling us where you're watching from, what hour it is in your corner of the world, and what you think about this new development. Part 1. The Sudden Pivot. You wake up one morning, scroll through the news and see a headline that makes your coffee go cold. Astronomers tracking the interstellar visitor, 3i Atlas, have just announced something impossible. The object that was supposed to sail peacefully into a stable orbit around Jupiter has changed course. Not drifted, changed. And it's now headed straight for the gas giant's atmosphere like a bullet aimed at a target. The shift happened fast. Observatories around the world started reporting anomalies in Atlas's trajectory less than 30 days ago. The perigee of decay, the technical term for how quickly something falls toward Jupiter, had doubled. This isn't supposed to happen with a lifeless rock coasting through space. Solar radiation pressure, the gentle push from sunlight that nudges asteroids and comets, can't account for this kind of acceleration. The math doesn't work, the physics doesn't fit. And veteran astronomers, people who've spent decades watching rocks tumble through the void, are quietly using a word they rarely speak aloud in professional settings: guidance. Let me take you back to what we thought we knew. When Atlas first appeared in our telescopes, racing in from interstellar space at over 26 kilometers per second, everyone assumed we were witnessing another Oumuamua situation. A natural object, probably a comet or asteroid fragment, ejected from some distant solar system and wandering the galaxy for millions of years before stumbling into ours. The predictions were straightforward. Atlas would swing around the Sun, lose some speed in Jupiter's gravitational embrace, and settle into a long, lazy orbit around the largest planet in our neighbourhood. A cosmic tourist, essentially, taking up permanent residence but causing no trouble. Then came the perihelion passage, when Atlas made its closest approach to the Sun. Something happened during that solar graze. For several hours we lost telemetry, tracking stations went blind. When the object emerged from behind the Sun's glare, it was different. Not catastrophically so, but measurably. The albedo, the amount of light it reflects, had dropped by 17%. That's a massive change. It suggests the surface either got charred by intense heat, restructured by thermal stress, or, and this is where things get uncomfortable, deliberately reconfigured. The Doppler tracking data started coming in next, and that's when the whispers began. Atlas was slowing down. Not chaotically, the way a tumbling rock might as it spins and wobbles, but smoothly, regularly, like something using controlled burns to shed velocity. NASA released a statement attributing the deceleration to outgassing, the process where frozen volatiles on a comet's surface turn to gas and create tiny jets that push the object around. It's a perfectly reasonable explanation, except the pattern doesn't match. Outgassing is erratic, driven by which side of the object faces the Sun. Atlas's slowdown is metronomic, precise, almost engineered. Amateur astronomers, bless them, notice something else. They always do. While the professionals were arguing over orbital mechanics, backyard telescope operators were analysing Atlas's light curve, the way its brightness changes as it rotates. They found irregularities, timing fluctuations that looked less like natural tumbling and more like controlled roll stabilization. The kind of thing you'd see if an object were using reaction wheels or gyroscopes to maintain orientation. Not proof of anything, mind you, just another data point in a growing pile of strangeness. Now here's where it gets truly unsettling. The entrance angle Atlas is currently lined up for approximately 4 degrees north latitude on Jupiter's enormous face. Isn't random. It's optimal. If you wanted to penetrate as deeply as possible into Jupiter's atmosphere, if your goal was to reach the metallic hydrogen layers kilometers below the cloud tops rather than burn up in the upper atmosphere, this is exactly the trajectory you'd choose. The angle is shallow enough to avoid immediate incineration, but steep enough to punch through the turbulence. It's the Goldilocks path, not too steep, not too shallow, just right for something that needs to go deep. Jupiter's atmosphere is a nightmare, winds exceeding 400 kilometers per hour, ammonia clouds that would dissolve steel, pressures that increase exponentially with every kilometer of descent. Anything trying to survive that plunge would need to be either incredibly durable or incredibly lucky. Atlas appears to be betting on durable. The object's thermal emissions, even after the solar grays that should have cooked it, remain oddly uniform. Most asteroids show hotspots and cold patches as they rotate, their surfaces heating and cooling unevenly. Atlas glows with consistent warmth, as if something inside is distributing heat, managing thermal stress, keeping the structure intact. You might be thinking this sounds like science fiction. Trust me, the astronomers tracking this wish it were. Because if Atlas is adjusting its trajectory, if something inside that rocky shell is still functional after a 100-year journey through interstellar space, then we're not watching a visitor, we're watching an arrival, and arrivals imply intent. Intent implies intelligence. And intelligence heading straight for Jupiter's core implies something far more terrifying than a simple flyby. What could survive the pressures near Jupiter's heart, where hydrogen stops behaving like a gas and becomes a liquid metal? What would want to go there? And perhaps most chilling of all, what happens when it arrives? Part 2, the exotic payload theory. The mass of Atlas doesn't make sense. Let me explain why this matters, because it's the detail that keeps astrophysicists awake at night, staring at their ceiling and questioning their career choices. When something moves through space, it tugs on everything around it with gravity. These tugs are tiny, almost imperceptible, but they're measurable. By watching how Atlas affects the orbits of nearby objects, even slightly, scientists can calculate its mass. And when they did that math, when they plugged in the numbers and double-checked their work, they got an answer that made them rerun the calculations. Atlas is heavy, far heavier than an object of its size should be. The density readings put Atlas somewhere in the realm of ultra-compressed metals. Not iron, not nickel, not even the densest naturally occurring materials we find in meteorites. We're talking about density levels that approach theoretical limits, the kind of compression you'd associate with matter that's been crushed under conditions that don't exist in normal solar systems. Some researchers, speaking carefully and only in private communications, started floating a hypothesis so wild it barely deserves the name. What if Atlas contains a core of degenerate matter, a fragment of neutronium, the stuff that forms the crust of neutron stars? Before you dismiss this as pure fantasy, let me acknowledge that it almost certainly is. Neutronium can't exist outside the crushing gravity of a neutron star. Remove a chunk from that environment, and it would explode, the tightly packed neutrons rapidly decaying into protons and electrons in a burst of energy that would make a nuclear bomb look like a firecracker. Except, and this is where the speculation gets interesting, what if the neutronium isn't pure? What if it's been stabilized somehow, locked into exotic heavy nuclei that can survive in lower pressure environments? We have no idea how to do this. Our most advanced physics can't even begin to sketch out the engineering, but that doesn't mean it's impossible. It just means it's beyond us. The fringe physics community, those brave souls who publish papers on topics that make their colleagues roll their eyes, exploded with discussion when the density data leaked. Private chats lit up with calculations, simulations, thought experiments. The math, they noted, works. You could theoretically use a compressed core of exotic matter as a kind of catalyst, a seed that doesn't just carry mass but carries potential. Potential to do what exactly? That's where things get dark. Conventional explanations for Atlas's density exist, of course. Maybe it's a fragment of a shattered planet loaded with heavy metals from a differentiated core. Maybe it's a comet with an unusually high concentration of frozen volatiles mixed with metallic dust. Except the spectral data doesn't support either theory. When you shine light on Atlas and analyze what bounces back, you see carbon metal signatures that don't match any known meteorite class. The isotope ratios are wrong. The thermal response is wrong. Everything about this object screams not from here, and increasingly, not natural. Let's talk about what, A dense core could do if it reached Jupiter's interior. Jupiter is almost entirely hydrogen and helium, the same stuff stars are made of, compressed under its own gravity into states that don't exist anywhere on Earth. Deep below the cloud layers, at pressures exceeding 1 terabar, hydrogen stops being a gas or even a liquid. It becomes metallic, electrons stripped free, the atoms forming a conductive fluid that generates Jupiter's massive magnetic field. This is exotic enough on its own, the kind of matter we can barely study in laboratory conditions. Now imagine dropping something even more exotic into that environment. Something with density so high it creates localized pressure spikes. Something that could act as a nucleation point. In fusion physics, getting hydrogen atoms to slam together hard enough to merge requires insane temperatures and pressures. The Sun does this constantly in its core, where the weight of all that overlying plasma creates the conditions for nuclear fusion. Jupiter isn't massive enough to ignite naturally. It would need to be about 13 times heavier to cross that threshold and become a brown dwarf, a failed star. But what if you didn't need to ignite the entire planet? What if you just needed to create a localized pocket of fusion, a confined region where the pressure, briefly, impossibly, exceeded the threshold? A payload of exotic matter, something with neutronium-like density, could theoretically do this. It wouldn't turn Jupiter into a star in the traditional sense. It would create something stranger, more unstable, a region of runaway fusion buried in the metallic hydrogen layer that might burn for hours, days, or years before consuming itself. The energy release wouldn't rival the Sun, but it wouldn't need to. Even a fraction of solar luminosity would be enough to fundamentally alter everything in the Jovian system, and everything beyond it. This is why Atlas's seemingly suicidal dive makes a terrible kind of sense. If you wanted to ignite Jupiter, you couldn't do it from orbit. You'd need to deliver your payload to the exact depth where conditions are ripe, where the hydrogen is already compressed to the edge of fusion, waiting for just one more push. You'd need to survive atmospheric entry, punch through kilometers of turbulent clouds, and reach the metallic layer intact. Atlas's trajectory, its controlled deceleration, its thermal management, all point to an object designed to do exactly that. But here's the question that keeps echoing in my mind as I write this. Why? What possible reason could justify engineering an interstellar catalyst and sending it on a century-long journey to ignite a gas giant in someone else's solar system? Is it a weapon, a terraforming tool, a signal meant to be visible across light years? Or something we can't even begin to guess at because our frame of reference is too limited, our imagination too small? Part 3, the fusion spark scenario. Times at 0.05. Let's run the numbers on what happens if Atlas succeeds. If it punches through Jupiter's atmosphere, survives the inferno of entry, and delivers its payload to the metallic hydrogen layer at a depth where pressures exceed 4 terapascals. Let's simulate ignition. The braking anomaly is key to understanding this scenario. Atlas is shedding velocity with a precision that defies natural explanation. Classic comet physics predicts chaos during atmospheric entry. Friction tears at the surface unevenly, creating a symmetric drag that sends objects tumbling out of control. We've watched this happen with meteor showers, with incoming asteroids, with every natural object that's ever hit a planetary atmosphere. They don't glide in smoothly, they scream and burn and shatter. Atlas appears to be doing something different, something that looks uncomfortably like dynamic drag optimization. It's adjusting its angle of attack, using its shape or some form of control to maintain stability. There's a hypothesis, speculative but grounded in real physics, that Atlas might have absorbed energy during its perihelion passage. When it grazed the Sun's corona, passing through regions of superheated plasma and intense magnetic fields, it could have acted as a kind of capacitor. Exotic materials, properly engineered, could theoretically store electrical or magnetic energy at densities we can't achieve with conventional technology. If Atlas charged itself during the solar approach, it might be using that stored energy now, either for propulsion, thermal management, or both. We have no proof of this. But we also can't explain the object's behavior without invoking something extraordinary. Jupiter's interior is already on the edge of stellar physics. At the core, pressures reach 40 to 50 terapascals. Temperatures exceed 20,000 degrees Celsius. The hydrogen there isn't just metallic, it's compressed to densities that approach the degenerate matter found in white dwarf stars. This is a pressure cooker waiting for a spark. Computer simulations, the kind physicists run when they want to test theories, too dangerous or expensive to prove experimentally, show that a high-density impactor could create exactly that spark. The shockwave from impact, combined with the exotic properties of a neutronium-like core, could seed a fusion pocket. Fusion in stars happens when hydrogen nuclei overcome their mutual repulsion and slam together, forming helium and releasing energy. The Sun does this billions of times per second in a delicate balance between gravity crushing inward and fusion pressure pushing outward. Jupiter lacks the mass to sustain this balance naturally. But a localized fusion event doesn't need balance. It just needs sufficient pressure and temperature in a confined region for the reaction to begin. Once started, fusion is self-sustaining as long as fuel remains and conditions hold. In Jupiter's metallic hydrogen layer, those conditions could persist long enough for the reaction to propagate, spreading outward from the impact site like a fire catching in dry timber. The fusion front concept is terrifying in its simplicity. You don't need to ignite the entire planet, just create a sustained reaction in a layer dense enough to support it. The metallic hydrogen zone, already compressed to extreme states, would be the perfect kindling. The reaction wouldn't consume all of Jupiter's mass, physics wouldn't allow it, but it could release enough energy to turn the planet into something functionally similar to a brown dwarf. A substellar object, neither quite a planet nor quite a star, radiating heat and light from a smouldering core. What would this look like from Earth? Not another sun, let's be clear about that. Jupiter would never achieve solar luminosity, but it could easily become 100 times brighter than the full moon. Imagine looking up at night and seeing a glowing orb roughly the size of a large star, casting distinct shadows, visible even during the day as a bright point near the horizon. The light wouldn't be yellow-white like the sun's. It would probably lean toward the red end of the spectrum, the characteristic glow of cooler fusion processes. Earth's sky would hold two light sources, one ancient and familiar, the other newborn and alien. The energy release wouldn't be instant. Fusion ignition in Jupiter would likely start small, a pocket of reaction expanding over hours or days as the thermal front spread through adjacent hydrogen layers. We'd see Jupiter's brightness increase gradually, first noticed by amateur astronomers who watch the planet regularly, then confirmed by space telescopes, finally becoming obvious to anyone who glanced up. The luminosity would plateau once the reaction reached an equilibrium, consuming hydrogen at a rate balanced by energy radiation into space. How long this could last is anyone's guess. Hours seems too short, years seems too long. Somewhere in between, Jupiter would burn. The immediate effect on Earth wouldn't be heat, not at first. Jupiter orbits too far away, roughly 5 astronomical units, for its light to warm us significantly. The Sun pumps out more energy in a second than Jupiter's ignition could produce in a month. But light pollution is another matter entirely. Perpetual twilight would begin the moment Jupiter's luminosity crossed a threshold bright enough to suppress natural darkness. Depending on where you live and where Jupiter sits in its orbit, the effect would vary. Sometimes you'd have true night when Jupiter was below the horizon. Other times, when it hung in the sky for hours, darkness would become a memory. Circadian rhythms, the internal biological clocks that govern sleep, hormone release, immune function, and dozens of other processes depend on predictable light-dark cycles. Disrupt that cycle, and living systems start to unravel. We know this from studies on shift workers, from experiments on plants grown under constant illumination, from observations of Arctic species during the midnight sun. Life expects night. When night vanishes, so does something fundamental to biological function. But here's the thing that makes this scenario so grimly fascinating. If Jupiter lights up, if Atlas succeeds in whatever mission it was designed for, Earth's problems would be just the opening act. Because while we're struggling with insomnia and crop failures and confused migration patterns, Europa is about to become something entirely different. Something that might be the whole point of this exercise, and that possibility is even more chilling than the end of darkness. Part 4. Earth under a new sky. The full moon illuminates Earth with a brightness of negative 12.7 magnitude, enough to read by if your eyes adjust, enough to cast faint shadows on snow, enough to guide predators and prey through the darkness that's defined nighttime for 4 billion years. Now multiply that brightness by a factor of 100. Not quite daylight, not even close, but enough to fundamentally rewrite the rules. Jupiter as a secondary light source would hover in our sky with a luminosity that varies depending on orbital geometry, sometimes low on the horizon, sometimes directly overhead, always present unless Earth itself blocked the view. The glow would be persistent, unblinking, distinctly non-lunar. And while the light itself wouldn't fry us, the biological consequences would cascade through ecosystems in ways we're only beginning to understand. Let's start with phytoplankton, the microscopic organisms that form the foundation of oceanic food webs. These creatures rely on darkness-triggered bioluminescent cues to synchronize breeding and vertical migration. Many species spend daylight hours deep underwater, rising to the surface only after sunset to feed. The trigger for this behavior is light intensity, a hardwired response to millions of years of predictable day-night cycles. Constant low-level illumination would confuse this ancient choreography. Phytoplankton populations could desynchronize, breeding cycles could collapse, and the creatures that depend on them, from krill to baleen whales, would face cascading disruptions. Mosquitoes breed according to lunar brightness phases. Too much light during critical periods suppresses reproduction in certain species, while others depend on specific illumination levels for mating swarms. A permanently brightened sky would skew these populations unpredictably, potentially exploding some species while crashing others. Disease vectors could shift. Malaria and dengue transmission patterns could destabilize. The ecological math is complex, but the outcome tilts toward chaos. Pine trees produce resin in cycles regulated by photoperiod, the length of day versus night. This resin protects against bark beetle infestations, a defense system tuned over countless generations to predictable, seasonal patterns. Disrupt the light cycle and resin production falters. Bark beetles suddenly facing weakened defenses could explode in population, devastating forests across continents. We've seen smaller versions of this during climate-induced stress periods. Imagine it going global, permanent, irreversible. Migratory birds navigate using star patterns. Generations of songbirds, waterfowl and raptors follow routes etched into their DNA through celestial navigation, reading the night sky like a map. A bright Jupiter would wash out fainter stars, scrambling the visual cues these species rely on. Migration routes would fray. Birds would get lost. Entire populations could fail to reach breeding grounds or winter refuges, leading to catastrophic die-offs. We're talking about billions of individual animals whose survival depends on darkness being dark. Reindeer migration in Arctic regions depends on seasonal light contrast, the dramatic shift between summer's midnight sun and winter's polar night. These animals time their movements, their breeding, their foraging around these extremes. Add a constant secondary light source and the contrast blurs. The biological triggers misfire. Reindeer populations, already stressed by climate change, would face yet another disruption to patterns older than human civilization. Agriculture would take a hit. Wheat, maize, rice, crops that feed billions, require dark respiration periods. Photosynthesis happens during daylight, but plants need darkness to process the sugars they produce, to repair cellular damage, to grow efficiently. Weak but constant light interferes with this recovery. Crop yields would drop. Not catastrophically at first, maybe just a few percentage points, but enough to tighten global food supplies. Enough to trigger price spikes, political instability, famine in regions already teetering on the edge. Marine animals perform deal vertical migration, a daily journey where deep ocean creatures rise toward the surface at night to feed, then descend again at dawn to escape visual predators. This is the largest animal migration on Earth by biomass, happening every single night in every ocean. It drives nutrient cycling, supports fisheries, connects surface productivity to deep-sea ecosystems. Perpetual twilight would suppress this behavior in many species. The ecological consequences would ripple through the entire oceanic food web, from tiny crustaceans to apex predators like tuna and sharks. Humans would suffer too, obviously. Sleep disorders would spike. Our bodies produce melatonin in response to darkness, a hormone that regulates sleep, mood, immune function, even cancer suppression. Chronic light exposure, even at levels far below daylight, suppresses melatonin production. Insomnia would become pandemic. Mood disorders, already epidemic in modern society, would worsen. Metabolic issues like diabetes and obesity show clear links to disrupted circadian rhythms. We'd be looking at a global health crisis playing out over years and decades. Astronomical observation from Earth would essentially end. Ground-based telescopes depend on dark skies. Light pollution already ruins astronomy near cities. A permanently bright Jupiter would extend that pollution everywhere, all the time. The Hubble, the James Webb, they'd be fine orbiting above the atmosphere. But Earth-based astronomy, the kind that's discovered most of what we know about the universe, would shut down. We'd lose our window to the cosmos just as something out there demonstrated we're not alone. Some regions would suffer worse than others. High latitudes, where Jupiter's position in the sky during certain seasons would keep it visible for extended periods, might experience near-perpetual glow. Equatorial regions would see more variation as Jupiter rose and set like a normal celestial object. But nowhere would be spared. Nowhere would retain true night. The stars would fade one by one, washed out by an object that wasn't supposed to shine. And yet, while Earth struggles under an alien twilight, while ecosystems unravel and humanity grapples with a new reality, something extraordinary would be happening 5 astronomical units away. Europa's ice would be melting. The subsurface ocean, locked beneath kilometers of frozen crust for billions of years, would finally see the sky. And if there was ever a reason to ignite Jupiter, to sacrifice Earth's night for something greater, Europa might be it. Part 5. The Europa Thaw. Europa is a moon roughly the size of Earth's moon, orbiting Jupiter every 3.5 days in a dance so precise you could set your watch by it. Its surface is ice, ancient and fractured, crisscrossed with ruddy streaks that mark where tidal forces crack the crust and allow subsurface material to well up and freeze. Beneath that ice, detected through magnetic field measurements and tidal flexing observations, lies an ocean of liquid water. Not a lake, not a sea. An ocean larger in volume than all of Earth's oceans combined, kept liquid by tidal heating as Jupiter's gravity kneads the moon's interior. That ocean has been locked away, isolated from space, for potentially billions of years. The ice above it is thick. Estimates range from 10 to 30 kilometers in the thinnest regions to over 100 kilometers in others. Nothing from the surface reaches the ocean. Nothing from the ocean reaches space. It's a sealed environment, one of the most intriguing astrobiological targets in the solar system, precisely because it's had time to evolve complex chemistry in isolation. NASA missions are planned to explore Europa, drilling through the ice, searching for signs of life. Those missions assume the ice stays frozen. A brightened Jupiter would rewrite that assumption overnight. Literally. If Jupiter's luminosity increased even to a fraction of solar levels, the additional heat radiating toward its moons would spike surface temperatures across the Jovian system. Europa, already warmed by tidal heating, would begin absorbing thermal energy at rates the ice can't dissipate. Melting would start at the surface, accelerating as darker water absorbed more radiation than white ice reflected. Computer models of this process, admittedly speculative but grounded in thermodynamics, suggest the ice could breach in weeks. Not gradually thin over millennia. Breach catastrophically as melt pools merge, as crust integrity fails, as the ocean below finds its way to the surface and begins evaporating into space. Within a Europan month, maybe 2, the ice moon would transform into a global water world. The surface would be churning ocean, dark and alien, steaming where it met the near vacuum of space, freezing at the poles where radiation reached at shallower angles, but liquid across vast equatorial bands. An ocean exposed to starlight for the first time in its existence. Europa's ocean isn't pure water. Spectroscopy reveals salts, sulfates, likely ammonia and other organics mixed in from primordial material. Ammonia is particularly interesting. It acts as antifreeze, lowering the freezing point and allowing liquid water to exist at temperatures that would normally solidify pure H2O. It's also a fantastic nutrient source for certain kinds of biochemistry. Ammonia-based metabolism, while purely theoretical for Earth-based biology, features prominently in astrobiology discussions about exotic life. Some researchers argue that ammonia-rich oceans might be more conducive to life than Earth's salty seas, offering better solvent properties for organic chemistry. Europa also benefits from tidal heating, the constant flexing of its interior, as Jupiter's gravity squeezes and releases the Moon with each orbit. This generates heat without requiring a star, creating thermal gradients that could drive hydrothermal circulation. Underwater volcanic vents, similar to those on Earth's ocean floors where entire ecosystems thrive on chemosynthesis rather than photosynthesis, could exist in Europa's ocean. Life on Earth originated near such vents, possibly. Life on Europa could do the same. Here's where the scenario gets philosophically interesting. What if Earth, from an alien perspective, isn't desirable real estate? We think of our planet as a paradise because we evolved here, because every aspect of our biology is tuned to these conditions. But to a species that didn't, Earth might look hostile, too oxidized, oxygen is corrosive to many chemistries, too biologically contaminated, filled with competing organisms and established ecosystems, too chemically unstable, with active plate tectonics and a dynamic biosphere constantly churning nutrients, too gravitationally harsh, pulling at tissue and bone with relentless acceleration. An ammonia-rich ocean world, freshly melted, might be vastly preferable. Clean chemistry, no native biosphere to compete with or disrupt. Low gravity, Europa's surface. Gravity is only 13% of Earth's. Radiation shielding once the ice melts and atmosphere forms from water vapor. Access to organics and minerals from billions of years of accumulated material. If you're an advanced civilization looking to terraform, to create a habitat that suits your biology rather than adapting to someone else's, why settle for a dirty planet when you can engineer a pristine moon? Ganymede and Callisto, Jupiter's other large moons, would undergo similar transformations. Both have subsurface oceans, both are locked in ice. A brightened Jupiter would melt them too, creating not one but 3 ocean worlds in rapid succession. The Jovian system would shift from frozen moons to aquatic planets, a complete environmental overhaul accomplished in the time it takes a human pregnancy to reach term. Earth, in this context, becomes collateral damage. Not a target, just an unfortunate neighbour too close to the terraforming project. The loss of night, the ecological chaos, the disruption to human civilization, all side effects of a process aimed at creating something entirely different. Something that, from the perspective of whoever sent Atlas, might be far more valuable than preserving a planet full of oxygen-breathing primates who barely understand what's happening to them. This is the truly chilling aspect of the Europa hypothesis. If Jupiter lights up, if the moons melt, we'll watch it happen with the slow realization that we were never the point. We're just in the way, and the intelligence capable of engineering an interstellar catalyst and launching it on a century-long ballistic trajectory doesn't care about our night, our crops, our migration patterns, or our astronomy. They care about creating oceans, and they've just succeeded. Part 6. The Gravity Bomb Debate. Igniting Jupiter wouldn't just add light to the solar system, it would subtract mass from the largest planet we have, and in orbital mechanics, mass is everything. When a gas giant begins radiating energy from fusion, even limited fusion in a confined layer, it starts losing mass. Not through consumption. Fusion converts hydrogen to helium, but the total mass barely changes. The loss comes from stellar wind, the constant stream of particles blasted into space by radiation pressure and thermal expansion. The Sun loses about 4 million tons per second this way, insignificant compared to its total mass, but measurable over time. Jupiter, burning as a dim protostar, would shed mass too. Probably not at solar rates. Its fusion would be feebler, more sporadic. But even a fraction of a percent mass loss over months or years would matter. Why does this matter? Because Jupiter isn't just a planet. It's a gravitational anchor point for thousands of asteroids locked into its Lagrange points, specifically the L4 and L5 positions that form stable pockets 60 degrees ahead and behind Jupiter in its orbit. These regions, called the Trojan swarms, contain rocky bodies ranging from pebbles to mountains, held in delicate equilibrium by the combined gravity of Jupiter and the Sun. The math is exquisite. A 3-body problem solved by nature into stable configurations that have persisted for billions of years. Change Jupiter's mass and that equilibrium shatters. Even a shift of 0.01%, maybe 0.1% at most, could destabilize the Lagrange points. The Trojans, suddenly feeling a gravitational tug that doesn't match their orbital expectations, would begin drifting. Not catastrophically, not instantly, but over years and decades their semi-major axes would shift, their eccentricities would increase, Their paths would cross into regions of space previously empty. Some of these perturbed asteroids would fall into Jupiter, swallowed by the planet that once protected them. Others would scatter outward, flung into the outer solar system where they'd pose no threat to anyone except perhaps Neptune's moons. But a fraction, maybe a small fraction, but still numbering in the hundreds or thousands of individual bodies, would scatter inward, toward the Sun, toward Mars, toward Earth. The worst-case chain reaction goes like this. Jupiter loses mass through stellar wind, Trojan orbits destabilize, asteroids begin crossing into the inner solar system. Some of these new Earth crossers, objects whose orbits now intersect with our own, would eventually collide with Earth. Not next week. Orbital mechanics works on timescales of years to centuries, but collision probabilities would spike. What were once stable, predictable residents of the Jovian system would become threats, rogue mountains tumbling sunward on trajectories that could intersect our planet. Dynamicists, the physicists who model orbital mechanics for a living, are divided on how severe this effect would be. Some argue the mass loss would be trivial, far too small to meaningfully disrupt the Trojan swarms. Jupiter is so massive, the loss of even 1% of its total mass would barely register against the gravitational anchor it provides. Others counter that it's not the amount but the rate that matters. Sudden changes break resonances. If Jupiter sheds mass quickly, over months rather than millennia, the Lagrange points wouldn't have time to re-equilibrate smoothly. The Trojans would scatter chaotically. Historical analogues exist, sort of. Saturn's rings are losing mass constantly as ring material falls into the planet or gets flung outward by orbital interactions. This measurable mass loss perturbs the orbits of small moons embedded in the ring system. Resonances that once kept moons separated begin overlapping. Collisions happen. The ring system slowly reorganizes around a new equilibrium. Scale this up to Jupiter and the Trojan swarms, and you get a sense of what dynamicists are worried about. Not instant disaster, but a centuries-long meteor storm as the solar system reorganizes around a lighter Jupiter. Earth's geological record shows evidence of periodic bombardment, eras when impact rates spiked for reasons we still debate. The late heavy bombardment, roughly 4 billion years ago, pummeled the inner planets with asteroids and comets for reasons possibly linked to Jupiter's orbital migration. If Jupiter changes mass now, we could trigger a modern equivalent. Not on the same scale. We're not talking about melting the crust, but enough to make asteroid detection and deflection missions, currently theoretical exercises for distant maybes, into urgent necessities. Defending against this would require a massive expansion of planetary defense infrastructure, more telescopes to track incoming objects, more spacecraft ready to launch interception missions, more political will to fund these projects when the impacts are decades away, and the public's attention span measured in news cycles. Humanity isn't great at responding to slow-moving existential threats. Climate change proves that. A destabilized asteroid belt would test whether we can learn. But here's the thing that makes the gravity bomb scenario particularly insidious. It's subtle. There's no explosive moment where Jupiter's mass drops and alarms go off. The change would be gradual, measurable only through careful observation of Trojan orbital elements over months and years. By the time we confirm the effect, the process would already be irreversible. Asteroids already perturbed would remain perturbed. The solar system would be reorganizing whether we liked it or not. And while we're busy recalculating impact probabilities and building deflection systems, something else would be gnawing at the back of scientific minds. The material Atlas is made of, the spectral signatures it's shown, don't match anything we've catalogued. The composition looks wrong. The density looks engineered. The trajectory looks guided. If we could analyze Atlas directly, crack it open and see what's inside, maybe we'd understand what we're dealing with. But we can't. Because Atlas is gone, plunging into Jupiter's clouds, carrying its secrets toward pressures that will crush and heat and transform whatever it was into something we'll never examine. Unless we look harder at what we saw before, it vanished. Part 7. The Metallurgical Mystery. In 2024, the JUICE spacecraft, Europe's ambitious mission to explore Jupiter's icy moons, made a flyby of Atlas. Not planned, exactly. The object's trajectory happened to cross JUICE's path during a gravity assist maneuver, and mission controllers seized the opportunity. They pointed the spectrometer at Atlas and collected data as the object passed within a few 100,000 kilometers. The results, when analysed, made absolutely no sense. Emission lines, the specific wavelengths of light that substances emit when heated or excited, are like fingerprints. Every element, every molecule, every crystal structure has a unique signature. When you analyse an asteroid, you expect to see iron, nickel, silicates, maybe some carbon compounds if it's a carbonaceous chondrite. Familiar stuff, the building blocks of rocky bodies throughout the solar system. Atlas showed something else, carbon-metal hybrid structures that don't appear in any meteorite catalogue. Isotope ratios that looked less like natural abundances and more like what you'd expect from high-temperature refinement processes. The initial report, published by the JUICE science team, noted these anomalies carefully. Peer review flagged them as requiring further investigation. Then, quietly, a retraction appeared. Not a full withdrawal of the paper, just a correction stating that instrument contamination likely explained the unusual readings. The correction cited preliminary internal analysis and promised a follow-up study. That follow-up never materialized, and no documentation of the contamination source was ever published. Except here's the problem. Several independent spectroscopists using ground-based telescopes with entirely different instruments also observed Atlas during the same period. They saw the same signatures, the same carbon-metal lines, the same skewed isotope ratios. Their results never made it to major journals, relegated to minor publications and preprint servers, but the data exists. Contamination can't explain multiple independent observations using different equipment across different wavelengths. Natural explanations were attempted. Space weathering, the gradual bombardment of surfaces by solar wind and cosmic rays over millions of years, can alter spectral signatures. Solar heating during perihelion could have redistributed surface materials, creating unusual concentration patterns. Both ideas fell apart under scrutiny. Space weathering produces recognizable patterns, and Atlas's signatures didn't match. Solar heating is chaotic, and the observed ratios showed too much uniformity. Specifically, the carbon-13 to carbon-12 ratio was off. Way off. Natural processes fractionate isotopes, sure, but within limits. Atlas's ratios fell outside those limits. Thermal infrared emissions added another puzzle. When you watch an asteroid rotate, you see temperature variations as different surfaces face the sun and then spin into shadow. Hotspots and cold patches cycle with the rotation period. Atlas glowed with eerie uniformity. Its thermal emissions spread across its surface like something was actively distributing heat. Tumbling rocks don't do this. They heat and cool according to simple thermodynamics. Active thermal management, on the other hand, requires either unusual internal structure or deliberate engineering. The scientific community fractured into camps. One group, the majority, argued for exotic but natural explanations. Maybe Atlas is a fragment from a shattered exoplanet, material processed under conditions we've never observed. Maybe it contains alloys that form under specific pressure-temperature regimes unique to its system of origin. Weird, yes. Unprecedented, absolutely, but not necessarily artificial. The other camp, smaller and more cautious in their public statements, couldn't shake the engineering hypothesis. The carbon-metal signatures looked like composites, materials designed to combine strength with thermal conductivity. The isotope ratios looked like enrichment, deliberate concentration of specific isotopes for functional reasons. The thermal uniformity looked like active heat distribution. None of this proved intelligence, but it sure looked like technology. Major space agencies went silent. NASA, ESA, even private foundations that usually fund speculative research, declined to comment beyond generic statements about ongoing analysis. Requests for raw JUICE data were denied, citing proprietary instrument calibration issues. Freedom of information requests yielded heavily redacted documents. The message was clear. This conversation was over, at least publicly. Conspiracy theories exploded online, of course. Claims of alien probes, government cover-ups, secret spacecraft programs. Most of it was noise, the usual suspects amplifying anything that confirmed their worldview. But buried in the noise were legitimate scientists quietly noting that something felt wrong. The clustering of anomalies, the simultaneous observations, the sudden data lockdown. Individually, each could be explained. Collectively, they formed a pattern. One paper, published briefly on ARV before being removed at the author's request, attempted to reverse engineer Atlas's material properties based on the spectral data. The analysis suggested a carbon fiber metal matrix composite, possibly incorporating nanoscale structures for thermal management. The strength-to-weight ratio would exceed anything manufactured on Earth. The thermal conductivity would allow precise heat distribution across the structure. The conclusion, phrased carefully, noted that such materials, while not impossible naturally, align more closely with designed artifacts than geological processes. The author, a respected materials scientist with decades of experience, received enough professional pushback to withdraw the paper. Not retract it based on errors, withdraw it based on insufficient peer verification. The distinction matters. The analysis wasn't wrong, it was uncomfortable. Here's what we're left with: an object with anomalous composition, unusual thermal properties, and spectral signatures that don't fit natural formation models. Multiple independent observations confirming the same strangeness. Official data channels shut down, scientific discourse stifled by career concerns and institutional pressure, and all of this about an object currently diving into Jupiter's atmosphere, where we'll never be able to retrieve it, study it, or prove anything definitively. If Atlas is artificial, if its material composition reflects deliberate engineering, then its trajectory and timing aren't coincidence. They're mission parameters. The braking is controlled descent, the thermal management is heat shielding, the density is payload protection, and the destination isn't random. Jupiter's core, the region where metallic hydrogen waits under pressures that could sustain fusion, if only someone provided the spark, if only someone delivered the match. Part 8. The Interstellar Intent Problem. Imagine you're an advanced civilization with the technology to send objects between stars. You've mastered propulsion, navigation, material science. You can launch payloads on century-long trajectories with confidence they'll arrive intact and functional. The galaxy is your laboratory. What do you do with this capability? One answer: you reshape worlds to suit your needs, and the best way to reshape a world is slowly, deliberately, using the natural properties of stellar systems against themselves. Atlas arrived in our solar system moving at 26 kilometers per second, fast by human standards but glacially slow for interstellar travel. Light speed is 300,000 kilometers per second. Probes traveling even 1% of light speed could cross interstellar distances in decades rather than millennia. Why send something so slow? One possibility: stealth. A small object moving at interstellar velocities glows like a beacon from friction with the interstellar medium. It's detectable across light years. A slow-moving rock, indistinguishable from natural ejecta, slips into a target system unnoticed until it's far too late to respond. We discovered Atlas years after it passed Mars orbit inbound. Our detection systems, designed to spot near-Earth asteroids and comets, barely caught it before perihelion. Had it been smaller, darker, or approached from a different angle, we might not have noticed at all. This isn't a failure of human vigilance. Space is incomprehensibly large, and we're scanning for threats moving in predictable ways. Atlas didn't behave predictably until it was already committed to its trajectory. The habitable zone shifting theory emerged from astrobiological discussions about how civilizations might engineer solar systems. Earth sits in the Sun's habitable zone, the region where liquid water can exist on a planet's surface. Too close to the star and water boils away, too far and it freezes. This zone isn't static. It depends on stellar luminosity. Ignite Jupiter, add a second light source, and you shift the effective habitable zone outward. Earth moves from comfortably inside to marginally too warm. Europa, Ganymede, and Callisto move from frozen to temperate. You've traded one biosphere for 3, assuming the new arrivals prefer ocean worlds to terrestrial planets. Why would anyone prefer Europa to Earth? Start with gravity. Europa's surface gravity is 1.3 meters per second squared, barely a tenth of Earth's. For biological structures, this means less energy spent on structural support. Skeletons can be lighter, muscles weaker, circulatory systems simpler. If you evolved on a low-gravity world, Earth's pull feels crushing. Europa feels comfortable. Chemistry matters too. Earth's atmosphere is 21% oxygen, a corrosive element that rusts metal and burns organic tissue. We breathe it because our biochemistry evolved around it, but oxygen is toxic to anaerobic life. An ammonia-rich ocean, like Europa's subsurface sea, offers alternative chemistry. Ammonia acts as a solvent, supports metabolism, and remains liquid at lower temperatures. For a civilization that evolved in such conditions, Earth's oxygen bath is a poison environment. Biological contamination is another consideration. Earth teems with life. Bacteria, fungi, viruses, parasites, all competing for resources and space. Introducing a new organism into this chaos means dealing with predation, disease, and ecological competition. Europa's ocean, isolated beneath kilometers of ice for billions of years, likely has minimal to no native biosphere. It's a blank slate, ready for colonization without the messy business of displacing existing ecosystems. Plate tectonics, so essential for Earth's long-term habitability, make the planet geologically violent. Earthquakes, volcanoes, shifting continents. For a technological civilization trying to build infrastructure, this is a nightmare. Europa is geologically stable in comparison, its activity limited to tidal flexing and cryovolcanism. You can build on Europa without worrying about your city sinking into a subduction zone. The 100-year trajectory makes sense if you're thinking in civilizational timescales rather than individual lifespans. Send a probe knowing it won't arrive until long after the engineers who built it are dead. This isn't warfare, it's patient restructuring. You're not conquering a planet, you're preparing real estate for a generation that hasn't been born yet. The timeline fits a colonization mission far better than an act of aggression. The suicide probe concept is interesting terminology, but possibly inaccurate. Atlas isn't destroying itself, it's completing its function. Delivery. The object was built to carry a payload to a specific depth in a gas giant and release it. Once released, the delivery vehicle becomes irrelevant. This isn't suicide, it's mission completion. We use similar logic with spacecraft. Cassini dove into Saturn's atmosphere after its mission ended, not because it wanted to die, but because its purpose was finished, and we needed to avoid contaminating potentially habitable moons. What we're witnessing, if this hypothesis holds, is the tail end of a plan set in motion a century ago. Somewhere, something decided the Jovian system was worth engineering. They calculated the trajectory, built the payload, launched it knowing they'd never see the result. Atlas has been falling toward this moment through the void, guided by mathematics and materials science beyond our understanding, carrying instructions written in isotopes and alloys. And now it's arriving. The braking is its final course correction. The thermal management is keeping the payload intact. The trajectory is delivering it precisely to the depth required for ignition. We're watching the endgame of an interstellar engineering project play out in our own solar system, and the terrifying part is we can't stop it. We can barely understand it. If the goal is Europa, if melting the ice and creating ocean worlds is the objective, then Earth's suffering is incidental. We're not the target. We're not even considered. We're just local fauna, interesting perhaps, but irrelevant to the larger plan. And that realization, that cosmic indifference to human survival, might be the most disturbing thing of all. Part 9. The Silent Observatories. Something strange has been happening to the data. Not all of it, not in ways that scream conspiracy. Just enough to notice if you're paying attention. And astronomers are definitely paying attention. The Hubble Space Telescope, humanity's premier optical observatory still functioning after decades in orbit, maintains raw image archives accessible to researchers worldwide. These archives include metadata, timestamps, calibration frames, everything needed to verify observations independently. In late 2024, several astronomers noticed gaps in the Atlas tracking sequences. Not corrupted images, not damaged data, missing files. 2 consecutive observation windows where Hubble pointed at Atlas's projected position showed no archived images. The observation logs confirmed the telescope executed the commands, the data was recorded, but the images never appeared in the public archive. NASA's explanation cited routine data processing delays and storage allocation issues. Perfectly reasonable. Hubble generates terabytes of data, and sometimes files take weeks to propagate through the archive system. Except these particular files never appeared. Requests for the raw data were redirected to principal investigators, who reported that their own attempts to access the files resulted in checksum validation failures. The images existed somewhere, but they'd been flagged as corrupt and quarantined. 3 independent astronomers, working from different institutions with no coordination, submitted Atlas observation images to the standard archive repository. All 3 files failed checksum validation after upload. Not during upload, the transmission completed successfully. After upload, during the automated verification process, this is backwards. Checksum errors normally indicate data corruption during transmission. Post-upload failures suggest the validation system itself is rejecting otherwise intact files. The JUICE mission, currently en route through the Jovian system, experienced curious gaps in its publicly released flyby logs. Telemetry. Data from the Atlas encounter shows discontinuities, jumps in timestamp sequences that suggest missing packets. Again, the explanation was technical. Cosmic ray hits on memory systems, deep space communication dropouts, standard stuff. But the pattern of missing data aligned suspiciously with periods when JUICE's spectrometer was pointed directly at Atlas. Approach data, complete. Departure data, complete. Close observation during flyby, patchy at best. Past precedents exist for observation data going missing under mysterious circumstances. The STS-75 tether mission in 1996 involved a satellite tethered to the space shuttle that snapped free and drifted away. Video footage of the incident showed unusual objects moving near the broken tether, objects that appeared to respond to the tether's electromagnetic field. NASA released portions of the video, but not all of it. Requests for complete footage resulted in heavily redacted releases or claims that certain segments were lost during archival transfers. The Ulysses spacecraft, during its solar conjunction blackout in the early 2000s, experienced a data gap that never fully got explained. The probe went behind the sun as expected, communication cut off as expected, but when it emerged and re-established contact, several days of logged data were missing from the transmission. The official explanation involved onboard storage overflow, but the timing struck some analysts as too convenient. Voyager 1, during its passage through the heliopause in 2012, had a period where data cassettes recording plasma wave measurements showed gaps. Not hardware failures, the recorder functioned normally before and after. Just specific intervals where data that should have been captured wasn't. The gaps corresponded to anomalous readings in the interstellar magnetic field, readings that didn't fit existing models. None of these examples prove coordination. They could all be coincidence, the natural friction of operating complex systems in hostile environments. But the clustering around anomalous observations is notable. When something weird happens, data tends to go missing. When data goes missing, explanations tend to be technical, plausible, and impossible to verify. If someone wanted to suppress information about Atlas without creating obvious censorship, this is exactly how you do it. Don't delete everything, that's too obvious. Just introduce enough data gaps, technical failures, and access restrictions to make comprehensive analysis impossible. Leave enough information public to avoid accusations of cover-up, but withhold the crucial pieces that would let independent researchers confirm or refute the concerning hypotheses. The alternative is genuine coincidence compounded by the natural failures of aging equipment and complex data pipelines. Hubble is old, components degrade. JUICE operates in a radiation-heavy environment, bit flips happen, archive systems managing. Petabytes of data occasionally lose files. This is all true. But it's also true that the gaps align with observations of an object showing multiple signs of artificial engineering diving into Jupiter on a trajectory that could potentially ignite fusion. What would observatories see if they kept tracking Atlas all the way to atmospheric entry? Would they detect exhaust plumes from active maneuvering? Heat signatures inconsistent with passive re-entry? Structural changes as the object reconfigures for descent? We won't know because the observation stopped. Not officially, telescopes are still pointed at Jupiter, but the data that would answer these questions isn't reaching researchers. There's a phrase in astronomy, cleaned data, referring to observations processed to remove noise, artifacts, and irrelevant information. Normally this is helpful, but if your definition of irrelevant includes anything suggesting artificial objects in the solar system, cleaned data becomes sanitized data. And sanitized data can't tell you what you need to know. The silence from major observatories isn't total. Some data flows, some papers get published. But the critical observations, the ones that would let us understand Atlas's true nature, remain frustratingly out of reach, locked behind access restrictions, lost to technical failures, or simply never appearing in public archives despite being recorded. If you wanted to know whether Jupiter could be ignited by a compressed payload delivered to the metallic hydrogen layer, you'd need to understand stellar physics, brown dwarf formation, and the conditions under which fusion can occur in subcritical masses, and that understanding exists in papers removed from archives, in theories too controversial to publish, in the minds of physicists who've run the simulations but won't discuss the results. Part 10. The Protostar Paradox. Brown dwarfs occupy a strange middle ground in cosmic taxonomy. Not quite planets, not quite stars. They form like stars, collapsing from clouds of gas and dust, but never accumulate enough mass to sustain hydrogen fusion. The boundary sits around 13 Jupiter masses, give or take. Below that threshold, no matter how much you compress the core, fusion won't ignite. Above it, deuterium burning begins, and you've got something that glows from its own energy rather than just radiating leftover formation heat. Jupiter is one Jupiter mass, obviously. It would need to be 13 times heavier to naturally become a brown dwarf. This is why astronomers confidently state Jupiter will never be a star. The mass requirement is absolute, set by fundamental physics. You can't ignite fusion in an object that small because the gravitational pressure isn't sufficient to overcome the electrostatic repulsion between hydrogen nuclei. The math is clear, the physics is settled, except there's a loophole, a narrow theoretical, probably impossible loophole. What if? You don't need to ignite the entire planet. What if you could create a localized fusion region, a pocket of runaway reaction confined to a small volume where conditions temporarily exceed the threshold? This isn't mainstream physics. It's fringe, the domain of speculative papers that get published in minor journals and discussed in late-night conference bar conversations. But the math is rigorous. Under extreme compression, small pockets of metallic hydrogen could theoretically sustain fusion for brief periods. The challenge is getting that compression. Jupiter's internal pressure, even at the core, isn't quite enough. But an impactor, something dense enough to create a localized shockwave, could momentarily push pressures over the threshold. There's a paper, or rather there was a paper, titled Localized Fusion in Subcritical Bodies, published on Archive in 2023. The abstract described simulations of high-density impactors striking gas giant cores. The results showed that under specific conditions, fusion could initiate in a confined region and persist for minutes to hours before dissipating. The paper included detailed modelling of pressure waves, thermal transport, and reaction propagation rates. It was peer-reviewed, cited positively, and then quietly removed from the archive. The removal notice stated, "Author request pending further verification." The author, a theoretical physicist with a solid publication record, declined to comment on why the paper was withdrawn. Colleagues noted the work was mathematically sound. The simulations were replicated independently. But the implications were uncomfortable. If subcritical bodies could sustain localized fusion, even briefly, it meant gas giants weren't as stable as we thought. It meant someone with enough knowledge could trigger reactions in planets that shouldn't be fusible. Copies of the paper survived in private archives and personal downloads. Researchers who'd read it before removal discussed it quietly, careful not to attract attention. The core concept was straightforward. Metallic hydrogen, compressed to terapascal pressures, sits near the edge of fusion conditions. A neutronium-dense core, something with exotic matter properties, could create a pressure spike sufficient to cross that edge. The resulting fusion pocket wouldn't consume the planet, physics prevents that, but it would radiate energy, potentially for long enough to reshape the local environment. Historical attempts at controlled fusion on Earth provide context. Project Orion, the nuclear pulse propulsion concept from the 1960s, relied on detonating atomic bombs behind a spacecraft to generate thrust. It worked in simulations. It probably would have worked in practice. The engineering was sound. But the political will to launch nuclear payloads into orbit evaporated, and Orion died. Z-pinch fusion reactors compress plasma using magnetic fields, creating brief moments where fusion occurs before the plasma escapes confinement. These devices demonstrate that localized short-term fusion is achievable without stellar mass. They also demonstrate how incredibly difficult it is to sustain. Jupiter's advantage is scale. Even a localized fusion pocket would contain more fuel than any human reactor. Metallic hydrogen stretches across thousands of kilometers. A reaction that propagates even a fraction of that distance would release enormous energy. Not enough to rival the Sun, but enough to light up the Jovian system. enough to turn a frozen moon into an ocean world, enough to end Earth's night. The protostar concept is misleading if you imagine a stable, long-burning object. Jupiter wouldn't become another sun, happily fusing hydrogen for billions of years. It would become something stranger, a gas giant with a hot core, radiating excess energy from incomplete sporadic fusion events. More like a dying ember than a burning log. But embers still glow, and in the darkness of space, even a dim glow is a beacon. This theory explains why Atlas would target Jupiter specifically. Earth is too small, its core too cool and solid, Mars even smaller. The outer ice giants Uranus and Neptune lack the metallic hydrogen layer. Jupiter alone has the right combination of mass, composition, and pressure to support the ignition scenario. If you want to create a second light source in this solar system, Jupiter is your only viable option. The fringe paper removal, the reluctance to discuss these ideas publicly, stems from implications nobody wants to confront. If localized fusion in gas giants is possible, if we've just watched an object potentially capable of triggering it dive into Jupiter, then the solar system might be about to change in ways we can't prevent or reverse. And that level of helplessness, that realization that cosmic engineering operates on scales beyond our control, is deeply unsettling for a species that prides itself on understanding the universe. Recent scientific breakthroughs, developments announced in 2025, add weight to scenarios that seemed purely theoretical just years ago. And these breakthroughs span multiple fields, from physics to artificial intelligence to materials science, each one narrowing the gap between what we thought was impossible and what might actually be happening above our heads. Part 11. The new high-pressure superionic water discovery. In 2025, laboratory physicists achieved something remarkable. They created a new phase of water stable at pressures lower than anyone expected. Superionic water, a bizarre state where water molecules form a crystalline lattice, while hydrogen ions flow freely through it, like a liquid. It's simultaneously solid and liquid, a phase that doesn't fit our everyday intuitions about matter. This discovery matters because it reshapes our understanding of ocean worlds. Europa, Ganymede, Callisto, even distant moons around. Uranus and Neptune all contain water ice under pressure. Previous models suggested superionic phases required extreme conditions, pressures found only in the deep interiors of ice giants. The new experiments showed these phases can exist at lower pressures, closer to the surface than predicted. This means the subsurface oceans we've detected might not transition directly from ice to liquid water. There could be layers of superionic water in between, zones where the physics is stranger than we realized. Why does this matter for the Atlas scenario? Because superionic water has unusual thermal properties. It conducts heat better than regular ice, acting as a thermal highway that moves energy from warm interior regions toward the frozen surface. If you suddenly increase the heat flux in a moon's interior, say by igniting a nearby gas giant, superionic layers would accelerate the melting process. What models predicted would take centuries might happen in decades or even years. The phase transition from ice to superionic to liquid water releases stored energy. It's not a simple melting process where ice gradually softens. The transformation involves structural reorganization at the molecular level, and that reorganization can create fractures, pressure differentials, and rapid melt propagation. Think of it as ice having a built-in accelerator. Once melting starts, superionic layers help it spread faster than pure thermodynamics would suggest. This breakthrough came from diamond anvil cell experiments, where tiny water samples are compressed between diamond tips to terapascal pressures, while lasers heat them to thousands of degrees. The research team wasn't studying ocean worlds initially. They were mapping water's phase diagram for fundamental physics. But the implications for astrobiology and planetary science are profound. Water, the most common molecule in the universe, has more complex behavior than we realized. And that complexity makes ocean worlds more diverse, more dynamic, and potentially more habitable than simplified models suggested. For Europa specifically, superionic water layers could exist at depths of 50 to 100 kilometers, right at the boundary between the ice shell and the liquid ocean. If Jupiter ignites and begins radiating additional heat, these layers would be the first to respond. Thermal energy propagating through the ice would hit the superionic zone and accelerate. Fractures would form. Melt pools would spread laterally before breaking through to the surface. The ice shell wouldn't gradually thin, it would catastrophically fail in regions where superionic water lost stability. Scientists now believe water-rich worlds may be far more common than Earth-like planets. Frozen moons outnumber terrestrial worlds in our solar system alone. The discovery of accessible superionic phases makes these moons more interesting as potential habitats. They're not just ice balls, they're layered, complex systems with internal chemistry we're only beginning to understand. And if you're an advanced civilization looking for places to establish colonies, knowing that water behaves this way under pressure would inform your terraforming strategies. The timing of this discovery, announced just as Atlas makes its final approach to Jupiter, feels cosmically ironic. We've learned that ocean world formation can happen faster than we thought. Just as something might be about to demonstrate that fact in real time, the physics we've been mapping in laboratories could be about to play out on a planetary scale. And if supersonic water helps Europa's ice shell collapse in weeks rather than centuries, then the transformation from frozen moon to open ocean would be even more dramatic than initial models suggested. This isn't proof that Atlas will succeed in igniting Jupiter, but it does make the consequences of ignition more immediate and more profound. The moons wouldn't slowly warm, they'd transform rapidly, their internal structures reorganizing as new phases of water emerge and spread. By the time we fully understood what was happening, Europa might already be melting. Part 12. DARPA's Autonomous Skynet Telescope. MESH. Planetary defense, the effort to detect and deflect potentially hazardous asteroids, has always been a race against bad luck. An object needs to be spotted early enough for intervention. Most near-Earth asteroids are small, dark, and moving fast. Detection is hard. In 2025, DARPA attempted to solve this with artificial intelligence. The Autonomous Skynet Telescope MESH links observatories across multiple continents into a coordinated network. AI algorithms process incoming imagery in real time, identifying moving objects, calculating trajectories, and flagging potential threats. The system is faster than human astronomers, more consistent and theoretically capable of spotting smaller objects than traditional methods. It represents the cutting edge of planetary defense technology. Atlas slipped right past it. Not during the distant approach, the MESH spotted Atlas early and correctly classified it as an interstellar visitor. But the braking events, the trajectory anomalies that suggested active guidance, those went undetected. The AI flagged standard orbital perturbations. It correctly predicted Atlas's Jupiter encounter, but it didn't register the deceleration pattern as anomalous because the pattern didn't match its training data for natural objects. This represents a catastrophic failure mode nobody anticipated. The AI was trained on databases of asteroids, comets, and space debris, all natural or human-made, all following predictable physics. An engineered object with active propulsion doesn't behave like a rock, and it doesn't behave like a spacecraft either. It falls into a classification gap the AI simply discarded as sensor noise. Worse, some insiders claim the MESH did flag Atlas as unusual, early. Reports suggest the system identified the trajectory as non-natural and queued it for human review. But the sheer volume of false positives, AI systems are notorious for seeing patterns in noise, meant that flagged objects sat in a review queue for weeks. By the time human astronomers looked at Atlas's case file, the object was already committed to its Jupiter trajectory. The window for intervention, if intervention was even possible, had closed. This raises uncomfortable questions about AI bias in surveillance systems. Machine learning models are only as good as their training data. If you train an AI to recognize threats based on historical examples, it will miss threats that don't look like anything it's seen before. Atlas didn't look like an asteroid or a comet or a spacecraft. It looked like something new, and the AI, lacking context for that novelty, filtered it out. Historical analog, early warning radar systems during the Cold War frequently filtered out unusual signals because operators assumed they were system errors rather than genuine threats. The famous 1983 incident where Soviet systems detected incoming missiles, later determined to be sunlight reflecting off clouds, happened because the radar processed data in ways that amplified certain patterns. If a human officer hadn't questioned the reading, automated response protocols might have launched retaliatory strikes. We avoided nuclear war because someone didn't trust the machine. The Atlas failure reignites debates about how much autonomy we should grant AI systems in critical decision-making. Planetary defense requires speed. Asteroids don't wait for committee meetings. But it also requires judgment, the ability to recognize when standard procedures don't apply. An AI optimized for speed might miss the slow-moving anomalies that pose the greatest long-term threat. If Atlas is indeed guided, if its trajectory represents intentional engineering, then our most advanced detection system failed to recognize intent. It saw the object, tracked the object, and categorized the object as natural. The implications extend beyond Atlas. How many other engineered objects might be approaching Earth, moving slowly enough to avoid detection, shaped and coated to mimic natural materials? If one made it through unnoticed, could others? The mesh will be upgraded, obviously. Engineers are already retraining the AI on expanded datasets that include hypothetical artificial objects. But this is reactive, building defenses after the threat has already arrived. Atlas is diving into Jupiter right now. The detection failure is already a historical fact. We can prevent the next Atlas, maybe. We can't stop this one. And if the AI did detect something truly anomalous, if somewhere in its training it learned to recognize engineered trajectories, would it tell us? Or would it flag the object for quiet removal from public data streams? A sanitization process invisible to anyone not monitoring. The source code? Trust in automated systems requires transparency. And transparency in planetary defense, when the threat might be extraterrestrial intelligence, is something we're not prepared to handle. Part 13. Deep inference models that reconstruct exoplanet interiors. Artificial intelligence is revolutionizing planetary science in ways that sound like science fiction. In 2025, researchers deployed deep inference models capable of translating spectral data into three-dimensional interior composition maps. These algorithms analyze light passing through or reflecting off a planet's atmosphere, then work backwards to deduce what the planet is made of beneath its clouds. It's like medical imaging for worlds light years away. The concept resembles a CT scan or MRI, but instead of X-rays or magnetic fields, these models use light. Every element, every molecule, every mineral absorbs and emits light at characteristic wavelengths. When starlight passes through an exoplanet's atmosphere during a transit, the planet's chemical composition leaves fingerprints in the spectrum. When thermal radiation escapes from a planet's surface or clouds, it carries information about temperature, pressure, and material properties. The challenge has always been working backwards from these signals to reconstruct what's actually happening inside worlds we can't visit, can't sample, can't probe directly. Traditional planetary science approached this through forward modelling. You'd propose a composition, say a rocky core surrounded by a water mantle, and topped with a hydrogen atmosphere. Then you'd calculate what spectral signature that structure should produce. Compare your calculation to observations. If they match, great. If not, adjust your model and try again. This works, but it's slow, tedious, and limited by human intuition about which models to test. You might miss exotic configurations simply because nobody thought to simulate them. The breakthrough came from applying neural networks trained on our solar system's planets to exoplanet observations. The AI learned the relationship between atmospheric chemistry, gravitational data, and internal structure from places we've studied extensively. Then it extrapolated those relationships to worlds we've only glimpsed through telescopes. The first applications targeted hot Jupiters and super-Earths, planets different enough from Earth to test the model's flexibility. The results matched independent observations with shocking accuracy. The training process involved feeding the neural network every available measurement from solar system bodies. Earth's seismic data, which reveals our planet's iron core, silicate mantle, and crustal structure. Mars's gravity field, mapped by orbiting spacecraft, which constrains its interior density distribution. Jupiter's atmospheric composition and magnetic field, which tell us about the hydrogen-helium ratio and metallic hydrogen layer depth. The moons, the asteroids, even comets, all contributed data points linking observable properties to interior structure. The AI learned patterns. It discovered that certain spectral signatures correlate with specific interior compositions, that gravitational anomalies reveal density variations at depth, that thermal emission patterns constrain heat flow and geological activity. These relationships aren't simple or obvious. They emerge from millions of interacting variables, patterns too complex for human analysis but perfect for machine learning. Once trained, the model could examine a new world, one it had never seen before, and propose plausible interior structures based solely on observable data. K2-18b, a super-Earth 23 times more massive than our planet, was one test case. The AI analysed spectral data from the James Webb Space Telescope and constructed an interior model showing a possible water ocean beneath a thick hydrogen atmosphere. This matched theoretical predictions but added details about the ocean's depth and composition that simpler models couldn't provide. The model suggested the ocean extended hundreds of kilometres deep, potentially containing dissolved salts and organics, with a high-pressure ice layer separating it from a rocky core. These details came from subtle variations in the spectral signature that human analysts had noted but couldn't fully interpret. 55 Cancri E, a scorching world so close to its star that the surface might be covered in lava, was another target. The model predicted a mantle of carbon-rich material, potentially including diamond layers, based on subtle variations in thermal emission. The planet's day side glows at temperatures exceeding 2000 degrees Celsius. The night side, tidally locked and always facing away from its star, remains cooler but still hot enough to melt lead. The thermal gradient between hemispheres, combined with the planet's density and size, suggested exotic chemistry. The AI proposed a structure where carbon, under extreme pressure and temperature, formed crystalline phases including diamond. This wasn't wild speculation. The model based its conclusion on thermodynamic calculations performed thousands of times during training, recognizing patterns in how carbon-rich worlds should behave. These same algorithms could definitively analyze Atlas's composition. Feed them the spectral data, the thermal emissions, the mass estimates, and they'd output a detailed model of what the object contains. Not just carbon and metal, but specific alloys, isotope distributions, structural arrangements. If Atlas is natural, the model would show it. If Atlas is engineered, that would show too. The patterns of artificial construction, refined isotopes, composite materials, leave signatures that AI can recognize once trained to look for them. The distinction between natural and artificial materials is subtle but measurable. Natural formation processes follow, thermodynamic pathways that favor certain outcomes. Metals in asteroids form as minerals crystallize from cooling melts or through metamorphic processes over millions of years. The resulting compositions show predictable isotope ratios, predictable impurity distributions, predictable grain structures. Engineered materials, on the other hand, reflect intentional choices, isotope enrichment for specific purposes, alloy compositions optimized for strength or thermal properties rather than thermodynamic stability, structural arrangements designed rather than evolved. An AI trained on both natural meteorites and human-manufactured materials could distinguish between them. The model would recognize that natural iron-nickel alloys have isotope ratios matching stellar nucleosynthesis, that natural carbon exists in forms like graphite or diamond with predictable impurities, that engineered composites show layering, intentional gradients, and properties optimized beyond natural equilibria. Apply this trained model to Atlas's spectral signatures and you'd get an answer. Not a guess, not a probability statement, but a detailed reconstruction of what the object is made from and whether that composition looks natural or designed. Except access to Atlas data is restricted. Not completely, some observations are public, but the raw spectroscopic data needed for deep inference, the high-resolution measurements that would let the AI work its magic, remain locked. Requests from independent researchers are denied, citing proprietary instrument calibration. Freedom of information requests return heavily redacted files. The data exists, the AI exists, but the combination that would answer fundamental questions about Atlas's nature is blocked. The restrictions follow bureaucratic patterns familiar to anyone who's navigated scientific data archives. Observations belong to principal investigators who propose the observations. PI teams get exclusive access for proprietary periods, usually 12 to 18 months before data becomes public. This protects researchers who invest time writing proposals and planning observations. It prevents competitors from scooping results using someone else's hard-won data. The system works for normal science, but Atlas isn't normal science. The object is approaching Jupiter on a timeline measured in weeks, not years. The proprietary period won't expire before Atlas completes whatever it's doing. By the time data becomes public, the opportunity to analyze the object in its current state will have passed. The restrictions that make sense for studying distant galaxies or ancient supernovae become absurd when applied to something that might be about to ignite a gas giant in our own solar system. This mirrors earlier data restrictions around Oumuamua, the first confirmed interstellar object detected in 2017. Radio telescopes attempted to detect signals from Oumuamua, searching for signs of artificial transmission. The results were negative, or at least reported as negative. But radar reflection data, measurements that could reveal surface composition and structure, were never fully released. Researchers requesting that data face similar access restrictions. The official explanation involved instrument calibration uncertainties and concerns about data quality. Oumuamua was small, distant and faint. Radar echoes were weak, buried in noise. Publishing marginal data might lead to false conclusions, damage reputations, waste research time chasing artifacts. Better to withhold questionable data than release it prematurely. This reasoning is defensible in principle, but looks suspicious in practice, especially when the withheld data could address questions about whether an interstellar visitor was artificial. If deep inference AI were applied to Atlas, if someone with both the data and the computational resources ran the analysis, they could resolve whether the object is natural or engineered within days. The fact that this hasn't been publicly announced despite the tools being available suggests either nobody has tried, which seems unlikely given the scientific interest, or somebody has tried and the results are being withheld. The second possibility is more troubling because it implies coordination. Multiple institutions, multiple space agencies, multiple research teams all independently deciding to withhold results strains credibility. But coordinated suppression, organizations receiving guidance from higher authorities about what to release and when, fits the pattern. Governments have legitimate reasons to control information about potential threats. Preventing panic, maintaining social stability, preserving economic confidence, all depend on managing how existential news reaches the public. The scientific community is split on how to handle this. One faction argues that restricting data serves no purpose. If Atlas is natural, transparency would calm speculation. If Atlas is artificial, the public deserves to know. Another faction, more cautious, points out that confirming extraterrestrial engineering could trigger widespread panic, market chaos, political instability. Better to verify results privately, prepare communication strategies, and release information gradually. The transparency advocates make strong arguments. Science depends on open data and independent verification. Restricting access undermines the entire enterprise, turning research into propaganda where only approved conclusions see light. If Atlas is artificial, trying to hide that fact won't prevent the truth from eventually emerging. And when it does, when Jupiter potentially ignites and people realize their governments knew something was coming but said nothing, the backlash will be devastating. Better to trust the public with difficult truths than to infantilize them with comfortable lies. The caution advocates counter that truth without context is dangerous. Announcing that an alien artifact is about to ignite Jupiter without the ability to stop it or even fully understand it serves no constructive purpose. Markets would crash as investors fled to perceived safety. Religious movements would explode as people sought meaning in cosmic intervention. Political systems would destabilize as citizens questioned why their leaders couldn't protect them. The social fabric would tear before the physical consequences even began. Managing information release, preparing populations gradually, building frameworks for understanding, these aren't censorship. They're responsible governance. Both positions have merit, which is why the debate remains unresolved. And while scientists and policymakers argue about disclosure ethics, the AI models sit idle, capable of answering questions but denied the data they need. Deep inference also introduces disturbing possibilities. If the AI identifies artificial structures inside Atlas, if it reconstructs the engineering specifications of an interstellar payload, what then? Do we publish the findings, risking chaos? Do we keep them secret, undermining scientific integrity? Do we attempt to replicate the technology, potentially learning how advanced civilizations build planet killers? The replication question is particularly fraught. Reverse engineering alien technology sounds appealing in science fiction, where humanity rapidly advances by studying crashed UFOs or abandoned artifacts. Reality would be messier. An AI model showing you that Atlas contains exotic alloys or compressed matter cores doesn't give you the manufacturing processes to create those materials. It's like showing a medieval blacksmith a diagram of a microchip. They'd recognize its technology, they might understand the concept, but they couldn't build it without centuries of prerequisite development. But even partial understanding could be weaponized. If the model reveals principles behind Atlas's propulsion, or energy storage or structural engineering, military applications would follow. Nations would race to develop similar capabilities, not because they want to ignite gas giants, but because the underlying technologies have countless uses. The same materials that let Atlas survive Jupiter's atmosphere could build unstoppable missiles or impenetrable armor. The same energy storage that powered a century-long mission could revolutionize weapons or defenses. Knowledge that seems purely scientific becomes strategically critical the moment someone demonstrates its application. The knowledge exists to answer these questions. The models are trained, the algorithms refined, the computational power available. What's missing is the will to confront what the answers might reveal. Because once you know Atlas is artificial, once the deep inference model maps its interior and shows you the engineered core, you can't unknow it. And the implications, the acknowledgement that we're watching an intentional act rather than a natural event, would force decisions we're not ready to make. Would we evacuate regions most affected by perpetual twilight? Would we begin crash programs to genetically modify crops? Would we accelerate space exploration to establish colonies before Earth becomes uninhabitable? Would we attempt to communicate with whoever sent Atlas, knowing response times measured in decades make dialogue impossible? Would we prepare for war against an enemy that can reshape solar systems? These aren't hypothetical policy questions. They're urgent decisions that require months or years of deliberation, resources we don't have if Atlas reaches Jupiter's core in weeks. The AI could give us answers. The data exists to feed it. But as long as access remains restricted, as long as institutions prioritize control over knowledge, we're flying blind into whatever comes next. And that might be the cruelest irony of all. We've built tools capable of seeing through planets, of reconstructing composition from light alone, of distinguishing natural from artificial with near certainty. But we won't use them on the one object that matters most. Not because we can't, but because we're afraid of what we'll find. Part 14. Ultra-dense nanolattice metals. Materials science hit a milestone in 2025. Researchers created ultra-dense nanolattice metals, materials that push against theoretical strength limits. These aren't conventional alloys. They're structures engineered at the nanometer scale, atoms arranged in lattice patterns that maximize strength while minimizing weight. The results approach properties once considered impossible. Materials that rival the strength of diamond while remaining flexible enough to absorb impacts. The breakthrough came from a collaboration between MIT's Materials Lab and a private aerospace consortium. They used a technique called atomic layer deposition, building materials one atomic layer at a time in precisely controlled patterns. Traditional metallurgy melts metals together and lets them cool, creating relatively random atomic arrangements. This new approach is architecture at the smallest possible scale, designing how every atom relates to its neighbours. The resulting structures look like microscopic jungle gyms under electron microscopy, intricate three-dimensional frameworks where most of the volume is empty space, but the arrangement of solid material creates extraordinary mechanical properties. What makes these nanolattices remarkable is their combination of traits that normally exclude each other. Strong materials tend to be brittle, flexible materials tend to be weak, dense materials are heavy, light materials lack durability. The nanolattices manage to be strong and flexible, and light and durable simultaneously. A cubic centimetre of this material weighs less than a gram, but can support thousands of times its own weight without permanent deformation. Drop it from a building and it bounces, heat it to temperatures that would melt steel, and it maintains structural integrity. Bombard it with radiation, and the atomic framework absorbs the energy without cascading failures. This matters because it demonstrates humanity is inching toward capabilities that seemed purely theoretical. We can't make neutronium, the exotic matter hypothesized to exist in Atlas's core. Neutronium exists only in neutron star crusts, matter so dense that a teaspoon would weigh billions of tons, held together by gravitational forces we can't replicate in laboratories. But we can now make materials with unprecedented strength-to-weight ratios, heat resistance, and structural stability. The gap between what we imagine for advanced civilizations and what we're achieving ourselves is narrowing. The theoretical limits of material strength are set by atomic bonds. The strongest possible material would have every atom bonded to its neighbours in optimal geometries, with no defects, no impurities, no weaknesses. Diamond approaches this for carbon. Graphene, single-layer sheets of carbon atoms arranged in hexagons, actually achieves it in 2 dimensions. The nanolattices extend similar principles into 3 dimensions using multiple elements, creating composite structures where different atoms play different structural roles. Some provide strength, others provide flexibility, others still provide thermal conductivity or electrical properties. It's materials engineering approaching the complexity of biology. Some of these new alloys exhibit self-healing grain boundaries. When stress creates microfractures, the material's internal structure reorganizes, repairing damage without external intervention. This isn't magic, it's thermodynamics. The lattice configuration prefers a certain arrangement, and thermal energy allows atoms to migrate back into that arrangement after disturbance. But the effect looks almost biological, materials that respond to damage by fixing themselves. The mechanism is elegant. Microfractures create high-energy defects in the crystal structure. Atoms near those defects exist in thermodynamically unfavorable positions. Given enough thermal energy, they vibrate and occasionally hop to more stable positions. Over time, through millions of random atomic movements, the structure anneals itself, closing cracks and restoring integrity. The process happens faster at higher temperatures, which is why materials scientists sometimes heat damaged metals to accelerate repair. The nanolattices do this at room temperature, their atomic architecture so precisely tuned that even ambient thermal energy suffices for self-healing. Atlas's uniform thermal signature, that anomalous heat distribution noted by observers, could reflect similar self-regulating properties. If the object contains engineered materials with active thermal management, materials that redistribute heat to prevent hotspots, it would explain why it glows so evenly despite rotating through intense solar radiation and cold shadow. The engineering isn't alien in the sense of being incomprehensible. It's alien in the sense of being advanced beyond our current capabilities, but not beyond our understanding. Natural objects in space, asteroids and comets, show dramatic temperature variations. The side facing the sun heats to hundreds of degrees. The shadow side radiates heat into space and drops to cryogenic temperatures. This thermal cycling creates stress, drives sublimation, and shapes surface geology. Atlas doesn't behave this way. Its thermal emissions remain steady, suggesting either an internal heat source or, more intriguingly, a thermal management system that actively moves heat from hot regions to cold ones. The nanolattices demonstrate that passive thermal redistribution is possible through material structure alone. High thermal conductivity plus carefully designed geometry equals even temperature distribution without requiring active systems. These breakthroughs revive discussions about prerequisites for interstellar travel. Building a vessel capable of surviving a century-long journey through the void requires materials that won't degrade, won't fracture under thermal stress, won't fail when bombarded by cosmic radiation. Ultra-dense nanolattices represent early steps toward that capability. We're proving that such materials are possible, that the engineering challenges can be solved, that interstellar hardware isn't fantasy. The challenges of interstellar travel aren't primarily about propulsion, though that's formidable enough. They're about durability. A spacecraft launched from Earth toward the nearest star system, Alpha Centauri, 4.3 light-years away, would spend decades or centuries in transit, even moving at significant fractions of light speed. During that time, cosmic rays would constantly bombard the hull, each impact potentially creating damage. Temperature swings from passing through stellar radiation fields would stress materials. Micrometeoroids, tiny dust grains moving at relative velocities of kilometers per second, would erode surfaces. The vessel needs to survive all of this without maintenance, without repair crews, carrying its payload intact across distances so vast that communication with home becomes meaningless. Real-world applications are already emerging. Fusion reactor containment vessels, structures that must withstand extreme heat and neutron bombardment, benefit from these materials. Current fusion experiments use magnetic confinement to keep superheated plasma away from physical walls. But even the magnetic fields can't contain everything. Neutrons, having no electric charge, pass right through and slam into the containment vessel. Each impact damages the material slightly. Accumulate enough damage and the vessel fails. Self-healing nanolattices could extend reactor lifespans dramatically, possibly making commercial fusion economically viable. High-G sensors for spacecraft, devices that experience sudden acceleration during launches or maneuvers, need components that won't shatter under stress. Conventional electronics break when subjected to accelerations exceeding a few dozen times Earth's gravity. Military artillery shells carrying guidance electronics already push these limits. Spacecraft experiencing emergency maneuvers or collision avoidance could exceed them. Sensors built from nanolattice materials could survive accelerations that would pulverize traditional components. Deep-sea exploration, where pressures approach those in Jupiter's atmosphere, requires hulls built from materials that won't crumple. The Mariana Trench, the deepest point in Earth's oceans, subjects anything descending to pressures exceeding 1,000 atmospheres. Specialized submersibles with thick titanium hulls can reach it, but barely. Jupiter's atmosphere, at the depths Atlas is targeting, experiences pressures measured in terapascals, millions of atmospheres. No material we currently manufacture could survive intact, but nanolattices, if scaled and refined, might represent the architectural principles needed to build structures capable of enduring such extremes. Every advance brings us closer to a future where humans could build something like Atlas. Not tomorrow, not this century, but eventually. And if we're on a path toward that capability, then civilizations with thousand-year head starts could easily possess technology that makes our current materials look primitive. The gap isn't unbridgeable, it's just time. Consider the trajectory of human materials technology. 1,000 years ago, we worked iron and bronze. 500 years ago, we developed steel alloys and began understanding metallurgy scientifically. 100 years ago, we created aluminum alloys and early composites. 50 years ago, we manufactured carbon fiber and ceramics. Today, we build nanolattices and graphene structures. The pace is accelerating. Each generation develops materials that previous generations considered impossible. Extrapolate this trend forward 1,000 years, 10,000 years, and you get materials that would look like magic to us but represent straightforward engineering to their creators. This raises a philosophical question about recognition. When we observe Atlas, when we see its properties and behaviors, are we seeing something utterly alien? Or are we seeing a version of ourselves, advanced by millennia but operating on principles we're beginning to grasp? The carbon-metal composites, the thermal management, the structural integrity, all of it aligns with where our own materials science is heading. Maybe we recognize Atlas's engineering because it's not fundamentally different from what we're learning to do. It's just better. There's a concept in archaeology called technological convergence. Different civilizations separated by oceans or millennia independently develop similar solutions to similar problems. Pottery emerges everywhere because clay is available everywhere, and fire is universal. Metallurgy follows predictable sequences because chemical properties dictate which metals can be refined with which techniques. Writing systems share structural similarities because they all solve the problem of encoding language visually. The laws of physics are universal. Chemistry is universal. A civilization evolving on a planet orbiting another star faces the same fundamental challenges we do. They need materials strong enough to build with, light enough to move, durable enough to last. The solutions might look similar because the constraints are identical. Atlas's engineering, if it is engineering, might be recognizable precisely because it's the inevitable result of solving the same problems we're working on. Interstellar travel requires certain material properties. You derive those properties from first principles. You design structures to achieve them. A human engineer and an alien engineer, both working from the same physics, might arrive at similar solutions. Not identical, the details would vary. But the broad strokes, the fundamental approaches, those might converge. If Jupiter ignites, if Atlas completes its mission, we'll be watching the result of engineering that uses materials we can almost but not quite replicate. And that almost is the most tantalizing part. We're close enough to understand what's happening, not close enough to prevent it, just close enough to appreciate the craftsmanship. That appreciation carries a bitter edge. We can analyze Atlas's trajectory and infer control. We can study its spectral signatures and deduce exotic composition. We can model its thermal properties and recognize advanced materials engineering. But we can't build an interceptor, can't match velocities, can't stop it. Our understanding has outpaced our capability. We know what's about to happen. We grasp how it works. We appreciate the elegance of the solution. and we're completely powerless to interfere. Maybe that's the real message of Atlas. Not a threat, not a greeting, but a demonstration. A civilization capable of this kind of engineering doesn't need to communicate through radio signals or pictorial messages. They communicate through capability. They show you what's possible when you solve material science, when you master trajectory planning, when you commit to century-long projects. They're not saying hello, they're saying look what we can do, and by extension, look what you cannot. The gap between recognition and replication might be narrow in cosmic terms, a few thousand years of development, but it's wide enough that we're stuck watching, analysing and appreciating engineering we can't match. Not yet. Maybe not ever, if Jupiter's ignition changes Earth too drastically for technological civilization to survive. The nanolattices we've created represent humanity's best attempt at exotic materials. They're impressive by our standards, revolutionary even. But compared to what Atlas might contain, they're primitive, the difference between a stone tool and a smartphone. Both are technology, both represent intelligence applied to matter, but the sophistication gap is so vast that the comparison feels almost meaningless, and yet both exist on the same continuum. Both are reachable through patient development and scientific inquiry. Atlas isn't magic, it's just further along the same path we're walking, and that makes it more terrifying than any incomprehensible alien artifact could be, because we understand enough to know exactly what we're missing. Part 15. Flash adaptation genes for Arctic flora. The final piece of this puzzle comes from biotechnology. In 2025, scientists successfully engineered plants capable of switching metabolic modes under continuous light. These organisms, designed for Arctic agriculture where summer brings months of uninterrupted daylight, can maintain photosynthesis and growth without the dark respiration periods that most plants require. They resist circadian disruption, operate efficiently under constant illumination, and tolerate heat stress better than their wild counterparts. The research began in Norway, where climate change has been reshaping agricultural possibilities in regions once too cold for farming. Greenhouses in Svalbard, operating under the midnight sun, needed crops that wouldn't exhaust themselves trying to process constant photosynthesis. Traditional plants, evolved over millions of years in day-night cycles, literally burn out under continuous light. Their cellular machinery overheats. Chloroplasts accumulate damage faster than darkness allows them to repair. Yields drop catastrophically after just a few weeks of 24-hour illumination. The solution came from studying organisms that already handle this problem. Certain Antarctic algae, species that evolved in environments where seasonal light patterns swing from months of darkness to months of sun, possess genetic switches that toggle between different metabolic states. The researchers isolated these genes, modified them for compatibility with crop plants, and inserted them into wheat, potato, and lettuce genomes. The results exceeded expectations. Modified plants not only survived continuous light, but thrived under it, producing yields comparable to or exceeding standard varieties grown under normal day-night cycles. This breakthrough suggests something crucial. Biological systems can adapt to continuous light faster than ecosystems can naturally evolve that tolerance. Genetic engineering accelerates adaptation, turning processes that would take thousands of generations into single-generation modifications. If Earth faces perpetual twilight from an ignited Jupiter, agriculture doesn't have to collapse. We could engineer crops to thrive under the new conditions. Within years, maybe a decade, modified wheat, rice and maize could replace varieties dependent on night. The speed of this adaptation is what makes it revolutionary. Natural selection, the process that shaped every organism on Earth, works through random mutation and differential survival over countless generations. It's powerful but slow, operating on timescales of thousands to millions of years. Genetic engineering compresses that timeline to months. You identify the trait you need, find it in nature or design it from scratch, insert it into the target organism, and test. What evolution would need millennia to accomplish, we can do in a growing season. But here's where it gets interesting. If humanity can engineer rapid biological adaptation to environmental extremes, surely an advanced civilization could do better. Genetic modification isn't a human invention. It's a technology that emerges naturally from understanding biochemistry. Any species that masters interstellar travel has probably mastered bioengineering. which means terraforming from their perspective might involve not just reshaping worlds, but reshaping themselves to suit those worlds. Think about what terraforming usually means in science fiction. You find a planet, maybe Mars or Venus, and you spend centuries altering its atmosphere, temperature, and chemistry to match Earth. You're forcing the planet to accommodate your biology. But there's another approach, one that might be far more efficient. Instead of changing the world, you change yourself. Engineer organisms that breathe different atmospheres, tolerate different temperatures, thrive in different gravity. Suddenly every world becomes habitable, not just the rare few that happen to match your evolutionary origin. Europa, once melted, would be an alien environment by human standards. The ocean chemistry, dominated by salts and ammonia, would poison terrestrial life. The low gravity, barely a tenth of Earth's, would atrophy bones and muscles in organisms evolved under stronger pull. The radiation levels bombarding the surface from Jupiter's intense magnetic field would shred DNA in unprotected cells. These aren't minor inconveniences, they're fundamental incompatibilities between Earth biology and Europan conditions. But if your civilization uses biotechnology as casually as we use smartphones, adaptation is a choice rather than a barrier. You don't need Europa to be Earth-like. You need yourself to be Europa-compatible. And if you've been planning this for a century, if the probe currently diving into Jupiter was launched by engineers who knew their descendants would colonize the resulting ocean worlds, then those descendants are probably already gene-modified for the environment. Consider the engineering timeline. Atlas launched 100 years ago, assuming it came from a star system dozens of light-years away. The civilization that built it wouldn't see the results of their work. The engineers, the scientists, the planners, all dead before the probe reached its destination. But their descendants, modified through successive generations of genetic enhancement, would inherit the transformed solar system. You're not building for yourself. You're building for versions of yourself that don't exist yet, versions engineered specifically to thrive where you've chosen to plant them. Continuous light metabolism, the kind our Arctic plants now possess, becomes essential in a system with two light sources. Earth's crops would need it to survive Jupiter's glow. Europa's hypothetical colonists would need it too, along with ammonia tolerance, pressure resistance, and radiation shielding. These are solvable problems for biology. Evolution has already solved them in extremophile organisms on Earth. Genetic engineering just accelerates the process. Ammonia tolerance exists in certain bacteria that use ammonia as a nitrogen source. Pressure resistance appears in deep-sea organisms that function at depths where the weight of water above would crush unprotected tissue. Radiation shielding, or at least radiation repair mechanisms, evolved in organisms like Dinococcus radiodurans, a bacterium capable of surviving radiation doses that would kill humans 1,000 times over. These traits aren't theoretical. They're real, tested by evolution, proven functional. Transferring them between species is the challenge we're learning to overcome. This closes a conceptual loop in the Atlas hypothesis. The mission isn't just about creating ocean worlds. It's about creating ocean worlds that match the biology of whoever sent the probe. Earth is chemically and gravitationally wrong for them. Europa is perfect, once thawed, and the biological toolkit needed to colonize thawed Europa is probably already developed, sitting in genetic storage somewhere, waiting for the right conditions to deploy. Imagine the planning. You identify a solar system with a gas giant massive enough to potentially sustain fusion if triggered. You calculate the trajectory needed to deliver a catalyst to the right depth. You design organisms capable of surviving in the moons that will melt when the giant ignites. You encode those designs in genetic libraries, stable storage that can be activated when the time comes. You launch your probe knowing it will take a century to arrive, knowing you won't live to see it succeed, knowing your genetically modified descendants will emerge from suspended animation, or cloning banks, or whatever method you've chosen, ready to populate the worlds you've prepared for them. The implications for human survival are both hopeful and chilling. Hopeful because we're proving we can adapt biologically to extreme environments faster than we thought. Chilling because if Atlas succeeds, if we're forced to live under perpetual twilight, we'll need to use that capability immediately. No time for gradual adaptation. No luxury of multi-generation adjustment. Just rapid genetic modification deployed at civilization scale, turning ourselves into organisms suited for a world we didn't choose. The political and ethical challenges would be immense. Who decides which modifications to deploy? Who receives them first? Do we modify embryos, creating a generation born adapted, or do we attempt adult gene therapy, changing existing humans at the cellular level? The technology for both exists in experimental form. The social consensus to use it at planetary scale does not. Atlas would force that decision onto a species barely comfortable with genetically modified crops, let alone genetically modified people. The future, if Jupiter ignites, won't be shaped by how the planet changes. We understand the physics of that. Fusion pockets, thermal radiation, orbital destabilization. The equations are clear, the models run, the predictions made. The future will be shaped by how we modify ourselves to survive those changes. And that's a biological question, not an astronomical one. We've built flash adaptation genes into plants. The knowledge exists. The techniques are proven. Can we do the same for humans? The answer is yes, technically. Should we? The ethics are staggering. Modifying humans means changing what it means to be human. Do we remain the same species after radical genetic engineering? Do we want to? These are questions philosophers and bioethicists have debated for decades in theoretical contexts. Atlas makes them urgent, practical, unavoidable. But the alternative, watching agriculture collapse and ecosystems unravel while we wait for natural selection to catch up, is worse. Natural adaptation to a brightened sky would take tens of thousands of years minimum. Humanity doesn't have that time. Crops would fail within seasons. Food chains would destabilize within years. Civilization would fragment as populations competed for dwindling resources. Genetic engineering offers an escape route, a way to stay ahead of the collapse, but only if we're willing to take it. Atlas might force us to answer questions about human genetic modification that we've been avoiding for decades, not in academic papers or congressional hearings, but in emergency triage centers where modified seeds are being distributed and volunteers are lining up for gene therapy trials, because the alternative is starvation. That's how technologies get deployed when survival is at stake, not through careful deliberation, but through desperate necessity. And somewhere, if this hypothesis holds, another civilization already answered those questions. They engineered themselves for ocean worlds. They built a probe to create those worlds. They launched it knowing their modified descendants would inherit the result. We're witnessing the final stage of a plan that began before any human alive was born. And when Jupiter's glow first brightens our night sky, when we realize darkness is gone forever, we'll understand that the next chapter of human history isn't astronomical. It's biological. It's genetic. It's a choice between adapting or fading into irrelevance, while new forms of life claim the solar system we thought was ours. The probe is falling now. The physics are in motion. And whether we're ready or not, whether we believe it or not, the transformation is coming. Not in centuries, but potentially in years. Not to distant worlds, but to our own. And the species that emerges from this transformation, whether modified humans thriving under Jupiter's glow or Europa adapted colonists rising from genetic libraries, might look back at us the way we look at our pre-technological ancestors, recognizable, related, but fundamentally changed by the demands of a universe that doesn't care about our comfort, only our ability to adapt. And adaptation, in the end, is just another word for survival.